So today we'll be talking about the interaction of atomic orbitals to form molecular orbitals. The first, we'll have a couple preliminaries here. The first is probably very familiar with two waves of two identical waves. If they interact with perfect constructive interference, then the high points of the waves add together to make points that are even higher at the end, and the low points add together to make points that are even lower at the end. Whereas if two identical waves interact with one another in a perfectly destructive way, they wipe each other out. This is going to be a good analogy for us when we talk about atomic orbitals interacting with one another in order to form molecular orbitals. So here's two hydrogen 1s orbitals. We have one centered here and one centered here. We'll call them A and B. They can interact with one another in a constructive way to form a bonding molecular orbital. This is called a sigma bond. You're used to that terminology. We will really soon see actually where that comes from. It comes from group theory. So this sigma bonding orbital. The important thing for the sigma bonding orbital is that we have more electron density between the two atoms now. So these electrons that started for individual hydrogen atoms on each one of the atoms now gets to, the two electrons get to share the two protons. And so that lowers the overall energy. We can take now the hydrogen 1s function for hydrogen A and hydrogen B and do a subtraction now. And this is destructive interference. And what this does is this lowers the amount of the electron density. So the amount of the electron density around these two hydrogens is actually, the electrons are getting to spend less time around the hydrogens than they would just in free hydrogen atom. So they're getting polarized out and away from the hydrogen atoms. So this is a less stable arrangement of two electrons than the two isolated hydrogen atoms would be. So we can talk about the simplest molecule, and it's the molecular ion that we're talking about. It's H2+, and it can be generated by shining the appropriate frequency of light on an H2 molecule. We can oxidize that H2 molecule. And what we're left with then is a highest occupied molecular orbital, the only one, the sigma bonding MO, has an electron in it. And then the LUMO is empty right now. So if we do our normal bond order that we would have talked about in general chemistry, the number of electrons in bonding MOs, there's 1, minus in antibonding MOs, there's 0. So 1 minus 0 over 2 gives us a bond order of 1/2. Well, let's see if this checks with things that we think about bond order. So the bond order in H2+ is weaker. Okay, it takes less energy to break the HH bond in H2+ than it does in H2. And the HH distance is longer. So in H2+, the HH distance is 1.06 angstroms compared to 0.74 angstroms in H2. So this bond order of 1/2 is longer and weaker than the bond order of 1 that's present in H2. So here's the diagram, and all these diagrams that we talk about will be set up this way. We have an atomic orbital on the left, we have an atomic orbital on the right. They interact with one another to form molecular orbitals. The only filled molecular orbital here is the HOMO. The highest occupied molecular orbital has 1 electron in it. The LUMO, the lowest unoccupied molecular orbital, is empty. This one has sigma bonding symmetry, and this one has sigma anti-bonding symmetry. A really important thing to point out here is the shading that you might see in the diagrams. So you can see this either as shading, or you can see it as a positive sign or negative sign on some of the atomic orbitals. The only thing that matters is being in phase or being out of phase. So the bonding, this is the sigma bond up here on top, being in phase can be shaded with shaded, or no shading and no shading. Okay, the point is that the phase of those two orbitals is the same. The two atomic orbitals are in phase. The two atomic orbitals are in phase. So these are totally equivalent to each other. Likewise, we could have shading on the left, no shading on the right, versus shading on the right with no shading on the left. The only thing that matters here is that they're out of phase. So this is the high energy combination on the bottom, the low energy combination here on top. Shading indicates the sign of the atomic orbital in the molecular orbital. These being in phase on top, those being out of phase on the bottom. A little bit later, we'll see that sometimes one of these orbitals will be larger than the other. When we get to that, the AO size, the atomic orbital size, reflects how much it's contributing to that molecular orbital. Talk about that more later. All right, well, we have three conditions in order for two atomic orbitals to interact and form molecular orbitals in a meaningful way. So they must have the same symmetry. They must have similar energy, and the closer the energy is for the two atomic orbitals, the stronger the degree of overlap, and they must have the spatial overlap. This overlap can come in two ways: the orientation of the orbitals, as well as the distance. So if we move these two hydrogen atoms across the room from one another, they're not going to interact with each other in a meaningful way. Okay, so like any model, the linear combination of atomic orbitals to make molecular orbital theory is only approximation of the exact electronic structure of molecules. All right, so it doesn't get much more exciting here for H2. So we have now both of the hydrogen atoms are coming in with an electron from hydrogen A, electron from hydrogen B. We get a bonding molecular orbital and an anti-bonding molecular orbital. We put an electron up and down in the bonding molecular orbital, and we leave the anti-bonding empty. Okay, and this now has a bond order of 1. From the Lewis structure, we could have figured that out also. We get a single line between the two hydrogens. So the Lewis structure theory and the molecular orbital theory here agrees really well. I'm not going to go through and read all this. This was definitely useful for you to look at. It basically says a lot of the things I've already said. It's sort of a summary slide. I'll send the slides to you. You can look at that for yourself. It gets a little bit more interesting here when we add a third electron. So if we take H2 minus, that system has 2 protons and 3 electrons. So 1, 2 electrons in the bottom orbital, 1 in the top orbital here. Now our bond order is 3 minus, excuse me, it's a 2 minus 1, which is 1 over 2. So we get a bond order now for this molecular anion actually for the bond order now is a half. So it's interesting that H2 plus has a bond order of a half, and H2 minus also has a bond order of a half. So either adding or removing electrons from this molecule decreases the bond order. It's very happy to be H2 neutral. Okay, so we'll go through these in a little bit more detail when we get to it, but I just want to go ahead and put this in as preliminary. The interaction between n atomic orbitals leads to the formation of n molecular orbitals. So here we have 1 atomic orbital, 2 atomic orbitals, so we have to end up with 2 molecular orbitals. If we started out with 3 and 2, if we started out with 5 atomic orbitals for a different molecule, then we would end up with 5 molecular orbitals. So the number of atomic orbitals going in will be the number of molecular orbitals coming out. Another important feature here is, the bonding orbital, the one that goes down, always goes down by a smaller amount than the anti-bonding orbital goes up. Okay, and so if I put a line through here, the distance from this middle up is larger than from the line down. And this is the case for every molecule. The energy up from the combined atoms is larger than the amount of energy going down. If the atomic orbitals are degenerate, and by degenerate we mean that if they have the same energy as each other, then how much they interact depends on how strong their overlap is. So if they have the same energy, depends on the overlap. And so this would be, for example, we have 2 atoms that are maybe close together. When we have those close together, they can overlap nicely. So we get a strongly bonding and a strongly anti-bonding combination. If I grab those 2 atomic orbitals and start to pull them apart, well, now the bonding orbital is only slightly bonding, and the anti-bonding orbital is only slightly anti-bonding. This is a summary of a few of the concepts we've talked about. This is a real simple way that molecular orbital theory can show you how it's okay for H2 to exist, but it's not okay for He2 to exist. So for H2, we've got two total electrons. Those two total electrons settle into a bonding molecular orbital. If I try to make dihelium, I have 4 electrons. 2 go into the bonding orbital, 2 go into the anti-bonding orbital, and so the bond order here is 0. And if we think back, if we want to think about this a little bit more deeply, the 2 electrons going up are going up more than the 2 that are going down. So this is actually worse than 0. These are forcing one another apart. And so that's why dihelium can never form. Here's a really important one. This will be what most of the rest of this talk is about. Orbitals must have the same symmetry. And when we get to the group theory part, that means they have to have the same irreducible representation to have non-zero overlap. So the overlap between the two is 0 if they're part of different irreducible representations. And it's non-zero if they're part of the same irreducible representation. All right, well, we'll talk about this mostly visually today, how that can work out. So both of these are in phase, and this is a bonding molecular orbital, like for H2. And here's an anti-bonding. So in phase, same phase, different phase, bonding, anti-bonding. Well, we can start to introduce some other orbitals, like p orbitals. And if the p orbitals are pointed right at each other, so the 2 shaded parts here are of the same color, they're the same phase, this is a bonding. This is also a type of sigma bonding, now between 2 p orbitals. If we turn both of those p orbitals, we get a different type of bonding. This is now pi bonding. So these are shaded in the same way. So there's a bond here, there's bonding interaction here and here. So, but it's a different type of bonding than the one to the left here. Okay, this is a type of pi bonding. What gets really exciting for metals, we get a third type of bonding. This is a delta, lowercase delta, and this is a face-to-face. So end-to-end, side-to-side, and now face-to-face interaction. And then down here, this is a dz squared antibond. This is a, let's say, what would this be? DXZ, XZ on both of the metals. This would be an antibond because they're out of phase. And this one here would also be a delta antibond because they're out of phase across. Well, this is probably how symmetry helps us the most. It shows us that there's some of the interactions are totally non-bonding. So this first one here, this is anti. So this is a sigma antibond here. So it's non-shaded right up against this shaded. So this is a change in phase. This is an antibond. But check this one out right here. So this is a non-bonding. This is totally, absolutely, completely non-bonding interaction. One way to say that is if I start right in the middle of the shaded and try to interact it here with the center of the 1s orbital, I'd get an antibond. But if I did the same thing here on the bottom, I would get a bond. And so it's equally bonding and non-bonding. So bonding plus equally non-bonding, we call that anti-bonding. Okay, here is another type of non-bonding that we would get between this dz squared and this this p orbital. Some of these, here's how some of these can get turned on and off. If we have 2 1s orbitals in phase and we start to stretch it, so if we start to stretch it out, then the overlap between the two and therefore the bonding decreases. So if they're really happy here at 1 unit apart, as I start to stretch it, I get this exponential decrease in the bond energy. Likewise, we have 2 p orbitals forming a pi bond here. And as I start to stretch this out, same sort of thing happens. The bonding, the overlap falls off, so the bonding falls off. Check out these perpendicular ones here. So if I try to take this PX and this PZ and have them interact with each other, I get a non-bonding interaction. There's an equal amount of bonding and anti-bonding, which we call non-bonding. It would be the same deal here. This one trying to interact with the side of this one would give me a a non-bonding interaction. When we have something like this, like a 1s and a 2p, it's interesting because at some locations, they are totally non-bonding. Okay, right here it's totally non-bonding. The overlap between the two at 90 degrees is 0. But if we were to walk this orbital around, so we start to walk it around, then it goes and becomes more and more bonding as we go around. Over here, this is just to show you also we have the same distance relationship if we have this interaction and we start to pull the two atoms apart. As we pull the atoms apart, the overlap decreases. So here's some different examples, and I'll probably end up asking y'all a question about some of these types of things. I'll give you a set of orbitals and ask you to say what is going on, to say whether it's bonding, anti-bonding, or non-bonding. So for example, a sigma interaction here, a pi interaction between two d orbitals here, a delta interaction, so end-to-end, side-to-side, face-to-face type interactions. I'll give you some and ask you to predict whether there's any kind of interaction, like this is non-bonding, this one's non-bonding, this one's non-bonding. All right, finally, back to something that you've seen before from general chemistry. We have a diagram that results from the interaction of the valence atomic orbitals on two fluorine atoms. The two s orbitals interact with each other to form a bonding and an anti-bonding combination. The 2pz orbitals interact with each other to form a strongly bonding and strongly anti-bonding set. And then the others, the px and the py, form a pi bond, and then a pi bond that looks just like a rotation of this. So oriented this way, then you rotate it by 90 degrees. They look identical to each other except for rotation, so a pi bond. This sigma 2 up here, this is a pi antibond. It changes phase across. And so sigma, sigma star, sigma, pi, pi star, sigma star. One really exciting, so simple molecular orbital theory predicts two unpaired electrons for O2. So if we go and we generate our diagram and we put 12 electrons in it, 2, 4, 6, 8, 10, and then by the Aufbau principle, we go up, up before we put any down in there, and so we get two unpaired electrons. And the naive Lewis structure that we would draw for this would have a simple double bond and would have no indication of any unpaired electrons. And O2 does have unpaired electrons. If you take liquid O2, it is attracted to a magnetic field. All right, we'll also talk more about this one next time. So if the atomic orbitals are non-degenerate, so they have different starting energies, they come, for example, from two different atoms, so we might have carbon and oxygen or something like that. I can name this one as oxygen because the lower lying one, this is lower in energy, it's more stable because it's on a more electronegative element. And so, for example, this would be carbon, this would be oxygen because oxygen is more electronegative. But the big thing that I want to point out here is that the bonding molecular orbital will look more like the lower energy atomic orbital, and the anti-bonding molecular orbital will look more like the higher energy atomic orbital. And that's why we have this swelling of the orbitals in the way that they are. So the fact that this is larger, okay, this lobe here on this side is larger, okay, because it is more of the lower energy atomic orbital. So this would be something like 4060, and then the upper orbital would be, say, 60% the higher energy atomic orbital, and it would be 40% of the lower lying atomic orbital. Another thing, this will be important for our next lecture. This is how the atomic orbital energies change as we go across a column. And I want you to notice that when we're up here at something like boron, the 2s and the 2p are relatively close in energy to one another. As we step across the period, carbon, nitrogen, oxygen, fluorine, the energy difference gets larger. That'll be really important for the next type of analysis that we do, is the fact that as we go from left to right across a period in the periodic table, that the 2s, 2p orbitals difference becomes larger. All right, we'll talk more about this next time also, but I wanted to show you a heterodiatomic molecule. That means one where we have two different atoms in there. So we have a hydrogen atom here on the left, we have a fluorine atom there on the right. And so the ones that are capable of engaging in a sigma bond are the 1s on the hydrogen, the 2s on the fluorine, and the 2pz on the fluorine. Well, it ends up that the 2s, 2p, as we had just said on the previous slide, difference is really large. And so there's almost very close to zero interaction between the 1s on the hydrogen and the 2s on the fluorine. And so this molecular orbital is basically the 2s fluorine atomic orbital. Well, then most of the bonding comes from the 2pz interacting with the hydrogen 1s to form a strong bond and an antibond. And what are we left with? So the other two, the px and py, are incapable of bonding to the hydrogen. So they go over with roughly the energy they had in the fluorine atom. So they come over as non-bonding. And what are we left with at the end of the day? 8 electrons, one that's basically in the 2s orbital on fluorine, 2 that are in the hydrogen fluorine 2p bonding orbital, and then 4 electrons that are sitting in the 2px and 2py orbitals on the fluorine atom. All right, and here's the kind of three things three types of molecular orbital diagrams that we'll see. If we have identical atoms like H2, we will get a strong bonding and a strong antibonding. If we get if we have two atoms that are similar to each other, two that are close to each other, so maybe nitrogen and oxygen that are right next door to each other, nitrogen and oxygen, the bonding orbital will look more like the oxygen, the antibonding orbital will look more like the nitrogen. So it's whichever they look, the molecular orbitals look more like whatever atomic orbital they're closer to. And then if we get very different atoms, so maybe hydrogen and fluorine, where there's a huge electronegativity difference, this molecular orbital can basically be an atomic orbital still on the electronegative atom, and then this orbital is mostly a atomic orbital on the less electronegative atom. If we push this really hard and had something like lithium and fluorine, which as you know is an ionic compound, this essentially would be 99.9% the lithium 2s orbital, and this would be 99.9% the fluorine 2pz orbital that we would have here.